In this area of quantum physics, we're going to look at what happens when energy comes into an atom and the electrons gain energy. Now, let's be clear about this. We're not talking about ionization. We're not talking about the photoelectric effect, which has got a photon coming in, giving energy, and an electron being raised to the surface and emitted from the surface, ejected from the surface of the metal. We're not talking about thermionic emission. We're going to look at a different effect where the electrons are going to stay inside the metal. They're just changing energy levels, changing shells, for example. So, with that clarification, let's get started. You've probably seen a rainbow, or a spectrum of white light broken into its component colours. You may even have seen a line spectrum, which shows the same pattern of colours, but is not continuous. We're going to look into why these lines are produced, and why different elements release different line spectra. Let's start with hydrogen. Hydrogen is a wonderfully simple element, especially if we take its simplest form: one proton and one electron. This drawing looks like we could be studying electric fields with a single point positive charge and a single point negative charge. Obviously, they're going to be attracted, but other forces are keeping them apart. So the electron will just stay here. If I try to pull the electron away, over here, I need to provide energy. So we say that the electron here has less energy than the electron here. Continuing, it has even less energy here, and here, and here, and, well, at some point I've given the electron so much energy that it leaves the proton completely. And that's what we call ionization. Now, I said that we are not talking about ionization, so I'm going to draw a line there and ignore it. So, what have we got left in the diagram? A positive nucleus at the bottom and 5 positions that I drew the electron at. It turns out that actually the electron can only exist in these 5 positions. Let's call them energy levels. We could call them electron shells if we want, but let's not. The way that chemistry and physics handle this sort of thing, at least at A level, is quite different. Let's call them energy levels. These energy levels are quantized, and to be honest, I don't really understand why. It's due to the wave behavior of electrons and how the wave function defines probabilities of existence. As I said, I don't really understand it, but I don't have to. Accepting it lets me use this lovely model of a hydrogen atom and, importantly, lets me explain and predict real-world behavior. It's a model. It's a model and it helps. So, we have the nucleus. I'm not interested in that, so let's just get rid of it. The first electron is here, and so this energy level, n equals 1, is called the ground state. It's the lowest energy state the electron can be in. These other levels, they are collectively known as the excited states, since they have more energy. If the electron moved from the ground state, n equals 1, to an excited state, n equals 2, we say that providing the electron with energy excites it to that level. If the electron drops back to level n equals 1, we say the electron relaxes as it releases energy. Gain energy, release energy. Gain energy, release energy. That's basically it. That's the model you need to understand. An atom, let's say it's an isolated atom, has energy levels. And electrons can only exist at those energy levels. If electrons gain energy, they can move to higher levels, and if they lose energy, they can move to lower levels. Right, so we have a model now, but we want to understand line spectra. So for that, let's bring in the photons. If we shine light on a material, there are a lot of things that can happen, from heating to the photoelectric effect and more. We're going to learn about one of those things, which is this. A photon can come in, interact with an electron, and the electron can absorb its energy. Remember, a photon is a packet of energy of electromagnetic radiation, so it's a little bundle of energy that hits the electron. The electron gets excited by this and, as you'd expect, well, this is where it gets a bit more complicated actually. Possibility A. The photon has exactly the right amount of energy and the electron moves neatly from n equals 1 to n equals 2. Nice, simple, so that happens. Possibility B. The photon has exactly the right amount of energy and the electron moves neatly from n equals 1 to n equals 3. Nice and simple, and that can happen. This needed more energy, but that's fine. It was probably blue compared to the original red. Possibility C. The photon has an amount of energy in between the first two. Maybe it is yellow. In quantum physics, the interaction must be complete. It's not possible to absorb half a photon. So what happens? The electron would get excited to somewhere around here, but there's no energy level, so it's not possible. This interaction is not possible. The photon cannot interact with this electron because it cannot pass its energy on. The photon continues through and out the other side. So in possibility C, the photon does not interact with the electron, it passes through. Actually, if you stop and think about it for a moment, that makes the material transparent. But for what we're talking about here, what this means is that this atom I have drawn here in my energy level model can only absorb certain photons. Photons with exactly the right energies, with exactly the right frequencies due to E equals HF, with exactly the right colours. How many are there? Well, we can go from n equals 1 to n equals 2, n equals 1 to n equals 3, n equals 1 to n equals 4, and n equals 1 to n equals 5. But we can also go from n equals 2 to n equals 3, n equals 2 to n equals 4, 2 to 5, 3 to 4, 3 to 5, and 4 to 5. That's 10 possible energies, 10 possible colours that can be absorbed. Now, what about relaxing? What happens there? Well, let's say we have an electron excited to level 2 and it relaxes. It loses energy, and it does that by releasing energy as a photon, a packet of energy of electromagnetic radiation. Obviously, the amount of energy is determined quite strictly by the difference in the energy levels. So it has a specific energy, and from E equals HF, it has a specific frequency, a specific colour. And, like before, there are 10 possible energies that can be released, from 2 to 1, 3 to 1, 4 to 1, etc., etc. 10 possible energies means 10 possible frequencies, meaning 10 possible colours. 10 possible colours can be released. This is the source of that line spectrum, which I mentioned at the beginning. This is why excited elements producing coloured light This is why excited elements produce coloured light, and why the colour that hydrogen produces is different from the colour that helium produces, or neon. They have different energy levels within them. They have different energy level jumps, so different absorption and emission spectra. If we look at other elements, we're going to get far more complex energy level patterns, and for molecules it gets messy. You might be wondering why it gets messy. Now again, I don't understand it, but if you remember that the quantized energy levels came about due to the wave nature of the electrons, well, if you have more electrons, you have more waves, more superposition, and that superposition creates complex patterns. It's along those lines. We've got a model that explains the spectra, but we want to try to get some maths. So what we want to do is give some values, give some energies to each of those levels. And that's what we'll do in the next video when we're looking at the energy levels in line spectra.